In today's lecture, we are going to discuss about the parameters which appear in fracture mechanics, and we are also going to discuss one of the derivations of one of the parameters. So, the field of fracture mechanics, in comparison to the other scientific fields or engineering fields, starts many of the researchers started before, but the field of fracture mechanics can be said to be starting from 1931 with the work of English, 1913. And you will see that there are glimpses of the parameter which appears in 1957, which becomes the most famous parameter, which was given by George Irwin. So English work is also he has taken inspiration from the work previously done, and what he described was and is known as stress concentration factor. And this stress concentration factor, the derivation we will not discuss, but we will see the importance of it. So if you have, for instance, a homogeneous material, and in this material you can imagine that if you apply forces like a tensile sample, then you can, so first of all you can imagine that it is a wired mesh. So it's something like this. You have a lot of wires, and these wires can behave like springs. And so if you put infinite number of wires, then it becomes the solid homogeneous material. So if you have forces in, say, y direction, and you have constrained it here that it cannot move in y direction, so uy is equal to 0 here, and you have given displacement, say uy is equal to 2 millimeter, or you can also give force as a boundary condition, so any value, say 200 megapascals. So what happens is that it stretches in elastic deformation, it stretches and it becomes thinner and longer. This part is well understood. Okay, so it becomes thinner and it elongates, and by how much amount it elongates, that can be calculated pretty easily following Hooke's law. But what if you have hole, and that hole Inglis makes in the form of an ellipse? And this is what becomes the trend afterwards, because he derived the work from another researcher which was done on circular holes, and English made it general. So circle is a special case of for an ellipse. So this elliptical hole has a major, so the radius in the major direction, let us call it Rx, is A, and radius in the minor direction is B. So this follows this coordinate system, and so this distance is A and this distance is B. You can visualize which one is B, and when A is equal to B, it becomes a circle. So now again imagine this wired structure, and these lines, you can imagine them to be the line of forces like in magnets. So away from the hole, these lines are passing as it should, but as you come closer to the crack tip or to the elliptical hole, these wires, like a curtain, they assemble at the tip of the ellipse, something like this. And if you have biaxial forces, so in this case the forces are in y direction, but if you have biaxial forces, then you will have lines passing through this also if you have forces in this direction. So you can see that in this region you have too many line of forces passing through a very narrow region. So you can say that force per unit area is going to be much larger here than a place which is away from the ellipse. So this English called stress concentration factor, and this factor is described as the stress which will be there at the tip of the ellipse is the applied stress into 1 plus 2a by b. And this 2a and b are major and minor distances from the origin for the ellipse along the major and minor directions. So this is applied stress. And if you convert this geometrically to the root radius of the ellipse, so if this is the ellipse, then radius of curvature here, if that is defined as rho, which is the root radius of the ellipse, then it can be described as, so the root radius can be described as b square by a. And so I can put b is equal to, or I can put a is equal to, so let me put b is equal to square root of a rho. So then if I replace this in the formula, then it becomes sigma applied, so sigma applied into 1 plus 2a divided by square root of a rho. So this becomes 1 plus 2 square root of a by rho. And when this crack is sharp, so in order to make this ellipse sharper, if this distance is b, then I just need to put b very close to 0 and go back to this equation. If b becomes very small, if it approaches 0, then this ratio becomes too large in comparison to 1, and therefore this can be approximated as sigma applied just 2a by b. So if I do that, then this goes away, and this can be written as sigma applied 2 square root of a by rho. So let me write the English stress concentration factor. It's not a factor, it's so the factor will be the ratio of this and applied stress. So sigma, so let me write sigma English. So sigma English is sigma applied, and then you have 2 root a by root rho. So keep this in mind, and then let us go to what happened when Griffith came. So Griffith's work is also very important, and that happens somewhere around 21. I might be wrong, but somewhere around that time. So what Griffith says is that in a body, so we again start with a homogeneous material which has a potential energy of pi, and then a crack is formed, and that crack is also something like this at the center. Not too much importance is given here on the dimensions of the crack, and this potential energy is pi naught, and this is the potential energy of the crack body because of the application of forces. So you have applied some energy to it, and Griffith uses the conservation of energy approach. So the potential energy pi can be written as the initial potential energy minus pi sigma square a square b divided by E. And this comes from linear elastic fracture mechanics. So if you have stress and strain relationship for a linear elastic material, that is just a straight line. And the amount of energy which is stored in the form of elastic deformation is the area under this curve, and that is simply half sigma epsilon. And this epsilon, if it follows this relationship in uniaxial direction, then it becomes sigma square by E 1 by 2. So, and then you see that pi a square comes if you have a circle with a radius of a. So never mind. So the rate of change in energy per unit crack length can be written as negative of pi sigma square, then this becomes 2a and b divided by e. So keeping this in mind, what Griffith says is that the rate of change of potential energy must be equal to the rate of change of surface energy with rate of change of surface energy which is being created when the crack is forming. So what Griffith says is the amount of energy which is given as an input to the system is consumed in formation of surface when a crack forms, and there is no dissipation of energy. That is his assumption. So the surface energy can be written as the surface which is being created. So out of nothing, this amount of surface is created, and if this length is 2a, then you have one surface here and another surface there, and approximating this to be equal to this length. So you will have 4a into b is the area of the surface which is created. So this becomes 4ab gamma s. Gamma s is the specific surface energy. So let me write this as S capital S, and so this becomes that. So the rate of change of surface energy, it's automatically correcting it, and so let me write it again. Del S by del A will be equal to 4b gamma s. So this must be equal to this, and well, so you can so then we have 4b gamma s equals to pi sigma square 2a b by e, and I'm taking only the magnitude, and so b gets cancelled and we don't have a here, so then sigma can be calculated as 4 gamma s e divided by 2 pi a square root of that. So this becomes equals 2e gamma s divided by pi a. So remember this relationship also. So here we have fine. So this is Griffith, and then comes Irwin, and we will derive this in detail, Irwin's formulation. But let me just give you the results first. So Irwin derives everything for a sharp crack, and at the tip of the crack the origin of the coordinate system is, and this is the distance from the crack tip, and he derives the function, the stresses, as sigma xx is equal to sigma root over pi a divided by root over 2 pi r cos theta by 2 1 minus sine theta by 2 sine 3 theta by 2. So let us call it, and then you have similar expression for sigma yy and sigma xy. So I can simply write in a normal way as sigma root pi a divided by root over 2 pi r f of theta. And this f of theta changes. So basically you have, if you want to find out the stresses at a point A on the material, then this distance is r and this angle is theta. So, and we will come to what the equation tells, but before that I want to see something. So he names this parameter. He gives a symbol k, which was given as an admiration to his friend. And if you compare this formula, so k is called stress intensity factor, which is sigma root pi a, and this k, let us look at, so this happened in 1957, okay, and you look at the Griffiths formulation, and you see that you have sigma root pi a here, which is a material property already. So if I just do cross multiplication, sigma root pi a is equal to 2e gamma s. E is a constant, gamma s is a constant, so this becomes a material property for very brittle, only elastic, linear elastic materials. But this is already there in 1921, and if you go back to 1913 English analysis, again you see sigma root a is there. You can add root pi because that's a constant, and you get again sigma root pi a in the expression. So this expression reappeared by many researchers, and finally this stress intensity factor formulation was used and is used, and this is in plane strain. It is called plane strain fracture toughness, and we'll discuss that why it is called plane strain fracture toughness. Okay, fracture toughness. Okay, so now let us start with the formulation first, and then we will discuss that why it becomes a material property in plane strain. So in order to do that, we need to understand Cauchy-Riemann equations, and we need to understand the stress functions. So Cauchy-Riemann equations, and we need to understand stress functions, and we need to also understand the basic behavior of the functions in stress strain space. So first of all, any function, we need to have stress equilibrium condition, and the stress so I think it is getting